Hey folks, I thought it might be worthwhile to make a video reteaching this factoring stuff. Fairly complicated topic. Once you get it, it's not as scary, but until you get it, it can be a little intimidating. So let's start off by reviewing what these things mean. What do we call this stuff? So we have a special name for each piece of this, what we would call a term in algebra. The first thing we have is called a coefficient. The number out in front of a variable is called the coefficient. We have also this thing that's called an exponent. This little power up here, you may call it a power. It's called an exponent. Now, some people would call the x a variable, but when a variable is raised to a power, it has another name. It doesn't have to be a variable, I guess. Anything raised to a power has another name called a base. Now, I want to get over those. We don't really talk about them a whole lot, but I do reference things like coefficient and exponent. So I think it's worthwhile to talk about this. So there's different kinds of factoring. The first kind of factoring that we're going to talk about is called GCF factoring. GCF factoring is never not first. Never not first. What that means is it's just kind of a funny way of saying that you should always try to GCF factor first. You should always try to look for this move first. So GCF factoring is where I look at something and I see if there's something in common that I can factor out, the greatest common factor, and factor that thing out. So as I look at 7x to the 6th and 35x squared, we have the coefficients that have common things, and then the variables with the exponents, the base and the exponent that have common things. So let's start with the 7 and the 35. Is there anything that goes into 7 and 35? Well, the answer is not 5. The answer is what goes into them, not what's left over. What goes into 7 and 35, the GCF, the greatest thing 7 and 35 have in common is 7. Then we look at the x's. We have an x to the 6th and an x squared. The greatest thing in common there is 2 x's. Now what we took out here, that's the GCF. What goes in the parentheses is trying to build back what we had before. So 7x squared times what would make 7x to the 6th? Well, 7 times, if I need a 7, I've already got a 7. I need 6 x's, I've got 2 x's, so that means I need 4 more x's. Now here we go again. I want to build back what I had before. I had a negative 35 and 2 x's. If I need a negative 35 and I already have a 7, that means I need a negative 5. 7 times negative 5 would make 35, negative 35. I need 2 x's. I already have 2 x's out front, so this is where we are. That's called GCF factoring. This piece right here, that's called the GCF. That's what we took out. And if you think about it, watch what happens when I distribute. 7x squared times x to the 4th is 7x to the 6th. 7 times negative 5 would be negative 35, and then I've got 2 x's. So it builds back exactly what we had before. Okay, let's have you try the next one on your own. Look at this and see if you can figure out what goes into both of 12 and 28. All right, let's see how you did. So I start off with 12 and 28. If you struggle with figuring out GCFs, well then you got to go into the margin and you got to start breaking stuff down. So I'm going to take 12 and I'm going to start to break down all the numbers that go into 12. 1 and 12, 2 and 6, 3 and 4. And then I'm going to take all the numbers that go into 28. 1 and 28. Start with the easiest one, 1 and 28. 2 works because it's even, 2 and 14. 3 doesn't work, 4 and 7, 5 doesn't work, 6 doesn't work, and 7 doesn't work. Now, the GCF is the greatest common number, the greatest number in any of these lists. So in this list, the greatest number that we have in common, we have a 2 that's in both lists, and we have a 4 that's in both lists, but the greatest one would be a 4. So 4 is what we would call our GCF. So I can GCF out a 4. And then I look at my x's. I've got x to the 3rd and x to the 5th. That means I have x to the 3rd. What would that leave as I go back. 4 times what would make 12? 4 times 3. I need 5 x's. I've got 3 x's, so I need 2 more x's. 4 times what would make 28? 4 times 7 would make 28. I want 3 x's. I've already got 3 x's when I distribute, so I don't need any more x's. Now, what you can do here is you can always just distribute this and see if what you got, if you distribute, see if what you got before, that means that you've done it correctly. So the next 2 examples are just kind of talking about little tricks along the way. If you look here, you don't always have to be able to take out a number, a coefficient. If you look at like 5 and 6, 5 and 6 don't have anything in common. So I can't GCF out let me see if that, yeah, it's a little bit better of a picture. So I can't GCF a 5 or a 6. They don't have anything in common, but they do have at least 2 x's. So you can just GCF a variable if you need to. You don't always have to take out a number with it. Again, you build back. 5x to the 5th. If I've got 2 x's, I need the 5, and I need 3 more x's. I'm trying to build 6x squared. I need the 6. I've already got 2 x's, so I don't need any more x's. Same idea with the next one. Again, I'm looking at it and I'm saying, all right, what do they have in common? What does 4 and 28 have in common? 4 and 28, this time 4 is the GCF. So I can take out a 4. And I look, x to the 4th and y to the 3rd don't have anything in common. This means that there are 4 x's. This means that there are 3 x's. They don't have anything. X's and y's are not common things. So in this case, I could only take out the coefficient. Okay, I want 4x to the 4th. That's what I want to build back. I've already got the 4, so I need x to the 4th. I want to build back negative 28. I've already got the 4. I need a negative 7. And then that needs to have 3 y's, so y cubed. Okay, so that's GCF factoring. GCF factoring is what we always try to do first. And then we look at what we have left over and we try to break it down some more. And that's where we get these other factoring methods. So let's move on to our next one. The next 2, actually, I'm going to kind of do in combination. Difference of perfect squares, which I call dopes, and sum of perfect squares, which I call SOAPs. So in both cases, we're talking about these things called perfect squares. So let's do a quick list of the perfect squares. Let's do the first 15. The first perfect square is 1, because 1 times 1 is 1. The second, 2 times 2, 4. The third, 3 times 3, 9. The fourth, 4 times 4, 16, and so on. 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10, 11 times 11, 12 times 12, 13 times 13, 14 times 14, 15 times 15. That list could go on and on forever. I would say everybody in Algebra 2 should know the first 12 by heart. Dopes works with these things that are called conjugates. The conjugates. And it's actually kind of easier, so I'm going to use the word conjugates here. It's actually easier for me to just show you the answer, or I think it is. I think it's easier to just show you the answer and have you work your way back to how we got there. So I'm just going to write down the answer to 4x squared minus 144 is 7x plus 12, and then 7x subtract 12. So first let's talk about what do I mean by conjugates. Conjugates are when you have the exact same thing except for the sign in the middle. This is a plus, that's a minus. The number in front is the same, 7x, 7x. After is 12 and 12, but one's plus and one's minus. Where did I get the 7 from? Well, what times what makes 49? 7 times 7 makes 49. Where did I get the 144? 12 times 12 makes 144. Now, why do we have to do the conjugates? It's because when you distribute, you want to get back what you had before. So when I distribute this, I would do 7x times 7x would be 49x squared. Then 7x times negative 12 would be negative 84x. 12 times 7 would be positive 84x. And then 12 times negative 12 would be negative 144. If you'll notice, what happens here is this middle part, negative 84x and positive 84x, cancel each other out, and you always are just left with the first part and the last part. That's what conjugates are. That's what dopes is. So when you get good, you can just look and you can just recognize that you're in dopes world. I know that I'm in dopes because what's special about 25 and 36? What's special about 181 or 4 and 121 and 49 and 144? These are all perfect squares. But we're going to talk in a second about what makes a sum of perfect squares different than a difference of perfect squares. So if I'm going to do a difference of perfect squares, we know it's going to be 5x and one of them is going to be positive. It's going to be 5x and one of them is going to be negative. I got 6 and 6 because 6 times 6 makes 36. Now, don't forget, just because we didn't do a GCF every time doesn't mean that you shouldn't still look for a GCF. 25 and 36 don't have anything in common, so I can't GCF anything out of them. As I look at this one, this doesn't feel like dopes because you don't have any perfect squares to begin with. But if you GCF out of 6, that leaves behind x squared minus 9y squared. And now all of a sudden I do have dopes. This is perfect square. That's a perfect square of 1x squared. That's a perfect square 9y squared. So this can then factor into dopes. 1x plus 3y. 1x minus 3y. Okay, so what makes SOAPs different? Well, SOAPs is the same as dopes, except it's a sum of perfect squares. So in other words, there's a plus in the middle. Well, let's try to factor this similar to what we did up above. So I know that it's going to be like this and like this. Okay, I know it's going to be 10x. Because 10x times 10x makes 100x squared. And I know 81 has got to be built out of 9 and 9. And so we have a little bit of a dilemma. We need to make this into a positive 81. Well, okay, and that's not that bad. Make it a 9 and a 9. 9 times 9 makes 81. Good. But the problem is, remember, this has got to cancel out in the middle. That means that you have to have conjugates. You can't have one B plus and the other one B plus because then it would add up to like 18. Well, you'd have to distribute, so it'd actually be 180, but whatever. So the point is you still need to have one B plus and one be a negative. So I still need one to be plus and one to be minus. But wait a minute. This still isn't going to work because 9 times negative 9 is negative 81, not positive 81. So what's the magic trick? What turns this negative into a positive? It's I. We have to put I's with these. Let me show you again. Not again, but let me just show you why does this work. Let's distribute and see what happens. 10x times 10x is 100x squared. 10x times negative 9i is negative 90ix. 9i times 10x is positive 90ix. And then here's the big one. Positive 9 times negative 9 is negative 81. That's bad news because it's supposed to be positive 81. But I times I is I squared. And you remember from a couple units ago, or a couple sections ago, I squared switches the sign. So then these cancel each other out. I have 100x squared, and I have a positive 81. So SOAPs is just conjugates. Again, they have to be conjugates. One has to be plus, one has to be minus, but they're conjugates with an I. So from here, pretty straightforward. You probably have the idea, I'm guessing. So now I got perfect squares again. Now, why is this dopes and this one SOAPs? It's because there's a minus in the middle here and a plus in the middle here. So this would break into 2x plus 11 with an I because it's SOAPs. And then 2x minus 11 with an I because it's SOAPs. Again, I want to try to factor this first. So if I look at it, I'm like, wait, these aren't perfect squares, but I've got something in common. 80 and 125 are both divisible by 5. X to the 6th and x to the 4th have 4 x's in common, so I can take out 4 x's. That would leave behind a 16x squared and a 5. Sorry, and a 25. God darn it. Got to redo my notes now. And a 25. 16, 25, those are perfect squares. I get 5x to the 4th, 4x plus 5i because it's soaps, 4x minus 5i because it's soaps. Okay, I'm going to pause here and then I'm going to do a second video for the second half of notes.